So we've explained what fossil fuels are, and they've got stored chemical potential energy. So how do we actually get that stored chemical potential energy and convert it into something that we would like to use? We burn it. We chemically react it. It's stored chemical potential energy. So we do a chemical reaction. That chemical reaction is with oxygen through combustion. And the stored energy in fossil fuels is in the form of hydrocarbon molecules, long molecules with oxygen, hydrogen, and carbon in them. And as we've said before, those atoms in those molecules are arranged in such a way that they can be thought of as having a bunch of compressed springs in them, and the electronic bonds between the atoms are compressing those springs. But if oxygen comes in and reacts with that chemically, it breaks those molecules apart to form new molecules that have less stored spring energy. They're less bunched up, and so the total amount of energy goes from being stored in scrunched up electronic springs into kinetic energy of the byproducts. So the energy transformation that takes place is from stored chemical potential energy into the kinetic energy of the molecules, the new molecules that are formed in the combustion. So if I'm reacting oxygen with hydrocarbons, it stands to reason that I'm going to make new molecules that have carbon and oxygen. So that's going to be carbon monoxide and carbon dioxide primarily, as well as hydrogen and oxygen, which is water. So as it explains in the slide here, it releases heat. That heat is just in the form of the kinetic energy of the molecular byproducts of the combustion. And those molecular byproducts are primarily carbon dioxide and water, also carbon monoxide. And then pollutants are the other things that are bound up in the fossil fuel that you're burning, that in this sort of energetic reaction that releases all of this stuff, now they've got kinetic, I'm breaking apart that substance, and so whatever other atoms, elements that are in there are also liberated and come out in the exhaust from that combustion. And that can include some things that are damaging to the environment, as we will see. Uh, so what are the particular technologies we use to capture that liberated thermal energy of those combustion byproducts? Well, you can start off with a simple one, which is an external combustion engine. And that is illustrated here with a steam locomotive where coal is burned to boil water, and the steam from that water then drives the pistons, which are connected mechanically to the wheels of the locomotive to make it move. So we're there seeing the direct transformation from stored chemical potential energy to the mechanical energy of the locomotive. More pertinent for our current society are fossil fueled power plants, thermoelectric power plants. And those are also essentially driven by external combustion engines, where what we have is, instead of with the locomotive, instead of the steam driving pistons to turn the wheels of a steam locomotive, we're instead using that steam uh, to spin a turbine, and that turbine is basically like a giant fan, and the steam is very hot. And you'll remember from the laws of thermodynamics that the more efficient to make that power plant requires a very big temperature difference between the thermal energy going into our machine and the cold side on the other side of the machine, which is the environmental temperature. So we want to make that steam as hot as possible. And so the boiler mechanism boils water and produces that steam, but the steam itself is then heated after it's boiled up to as high a temperature as possible. And it's carrying then a lot of kinetic energy to go by this fan and really provided a lot of kinetic energy. That fan, that turbine, is just mechanically connected to a generator. And as we've illustrated in some of the demonstrations that you've watched, if I have a motion of a conductor in the presence of a magnetic field, that magnetic field will cause the electrons in that conductor to move. And that's just the definition of electrical current. So the particular configuration that is set up is to have a big coil of wire spinning inside a magnet. And that big coil of wire is connected to that turbine. It spins, and as that coil spins inside the magnet, it produces an electric current through the coil, which we then connect to our electrical grid. The steam that passes by the turbine comes out with less energy. It's given a lot of its energy to the turbine, as we've learned from the law of thermodynamics. It can't give 100% of its energy to that because a lot of that thermal energy in the steam is incoherent. It's the random motions of the molecules of water. And so the, the steam that passes by on the other side is still warm, and we have to cool it off before we dump it into the environment. But usually you'll see these power plants near a natural body of water, and that body of water is the source for the water that is being boiled to produce steam, and then it is also the dumping ground for the warm water that comes out after it has passed by the turbine. And usually after going through a cooling tower, as shown in the slide here, to bring the evaporation, remove some more of the thermal energy from that water so that it's not too hot to kill all the life in the rivers or the lake. An internal combustion engine we're familiar with in our car. It's still the same basic idea. We burn the fossil fuel, gasoline, that produces a thermal energy of a vapor cloud. That's the exhaust, the combustion products of that fossil fuel. And that hot expanding gases drives a piston. And we're actually doing, unlike in a steam locomotive, we're doing the combustion inside the piston chamber, and the gases then directly push the piston up and down, which is connected to a crankshaft, which is ultimately connected to the wheels of the car. So if we take a look at automobiles, which is one of our major sources of energy and use of fossil fuels, there's lots of places where the energy gets spent. So this figure shows a fairly sobering diagram of the energy flow. If we take the energy that goes into the engine, because of the second law of thermodynamics, 62% of that energy that is available theoretically in the stored chemical potential energy of the fuel is wasted. That's due to the second law of thermodynamics and entropy, and that equation that we saw in the last module, E equals 1 minus TH over TC. And so 1 minus T, the efficiency is bigger if TH is bigger. So it's 1 minus TC over TH. And sorry about that. And so it's 1 minus the cold temperature over the hot temperature. In any event, it's less than 1. And the amount that it's less than 1 has to do with the difference in the temperature of the combusted products and the temperature outside. So for our gas-powered cars, 62%, almost 2/3 of the energy is wasted. So that leaves 38% left over. Roughly half of that 38% goes to friction in the engine itself. You've got pistons sliding up and down inside the engine. So half of the energy goes into overcoming friction in the car engine only. So we haven't even gotten to the car moving yet, just in the car engine. And so that's only leaving 20% left of the original energy, 2% to power things like your lights, radio, air conditioner, things like that. Now I'm down to just 18% of my original supply to make the car move. Then this 3% friction that's shown underneath the central box, that's the friction of the wheels on the road and the air actually not even the air resistance, that's just the friction of the wheels on the road. So only 15% of the energy available in the gasoline goes to moving the car, and and then we stop the car, have air resistance is where all that energy ultimately goes. So ultimately, you can see it's all going to thermal energy in the end. Friction, friction, friction. Brakes are friction, air resistance is friction, thermodynamic losses, it's all going to thermal energy. Um, this figure just illustrates different levels of fuel efficiency in terms of how much useful kinetic energy we get from different types of fuels with different sorts of car technologies. And of course, now we're seeing more and more electric vehicles on the road, which are potentially using fossil fuels at a power plant to produce the electricity to make them go. But the fossil fuel power plant has a much higher efficiency than the uh, fossil fuel power plant, essentially, that is a gasoline powered engine in your car. Diesel engines, just a note, are internal combustion engines in a car, but they work on a different principle with a different grade of gasoline. And because of that, they burn at a higher temperature. Since they're burning at a higher temperature, that efficiency, 1 minus Tc divided by Th, big Th in the denominator makes that part that gets subtracted off the 1 a smaller number. So diesel engines are inherently more fuel efficient. However, because of the chemistry of the diesel gasoline and that higher combustion temperature, they're more polluting. So I can go farther on a gallon of diesel gas, but I'm going to be producing more pollutants when I do so. A lot of hybrid cars out there now, and what those hybrid cars do is they work on reducing some of these losses that you see here when you brake. That energy of braking, instead of just being wasted as thermal energy, gets put back into a battery, which can then be used to power the transmission or the drivetrain of the car. So the hybrid vehicles are capturing some of these other um, losses of energy and recycling them back into a battery that helps improve the fuel efficiency. And then, of course, there are pure electric cars. Um, we've mentioned previously also that we can have combined cycle power plants where the waste that comes out of the first power plant is still warm. And so if we heat that up, we've already sort of got a head start on getting that waste steam and water up to a higher temperature to run a second turbine and run a second generator. And the overall efficiency of that combined power plant can be higher than one with just a single one. But ultimately, you're limited by that equation. And that equation has ultimately got a limit that's set by the temperature of the Earth, which is about 300 Kelvin.